Hello everyone, my name is Belma and I'm going to present our paper Sequential Zeroing Online Heavy Hitter Detection on Programmable Hardware. So first let's start with defining what a heavy hitter is. Heavy hitters are flows that transport most of the traffic inside a network, and in this paper we define them as flows that have exceeded a threshold number of packets in the sliding window of last n packets. However, why are these flows this important? So first, they form most of the traffic inside the networks, thus they're also the most important ones for traffic engineering. In addition, they're very important for many networking applications. So for example, denial of service anomaly detection or flow size aware routing. So the main goal of our paper was to detect whether a packet going through a switch is part of a heavy hitter flow or not. In addition to this, we set a few other goals that I would wish to emphasize here. First, we wanted to do so online. So we wanted to be able to deploy our algorithms on the switches themselves. This way, the switch can make a decision or apply custom actions on the packet depending on whether the packet belongs to a heavy hitter flow or not. In addition, we wanted an algorithm that can support sliding windows. So we wanted to have a mechanism that would allow us to remove outdated flows from the counting sketch. So we want to have an accurate online detection, but to do so we need to keep track of the most recent heavy hitters. And as time passes, different flows become heavy hitters. And so an addition of the sliding window will actually address these problems and would, by only keeping the counts that belong to the last n packets that are processed by the switch in the counting sketch. However, also to be able to deploy these algorithms on the switches, we need to take the constraints of the programmable hardware into account. So this figure shows a typical processing pipeline of a programmable switch. We can see that each incoming packet is processed through a set of stages. So in each of these stages, we can apply some simple actions on packets. So for example, we can do additions or bitwise logic, or for example, hashing. However, loops and more complex actions are not possible. In addition, each of the stages has a certain amount of memory that can be used to keep state. So for example, flow counts. However, as packet passes through the stages, it can only access this stateful memory once. Of course, in addition to all of this, we want to have a low memory footprint because, of course, we are running these algorithms on the switches and they also have a limited memory. So I'm first going to explain a few problems that exist with the current related work. There were a few algorithms that were developed with programmable switches in mind. However, they have a few shortcomings. So first, none of these algorithms includes a mechanism to count over sliding windows. The way this is usually done is an interval-based approach. So after a certain amount of time, all the registers, so all the counters are flushed, so they're reset to 0, and the counting starts from the beginning. However, in addition to this, some of them, such as HashPipe, also have problems to compute an online estimate when counting over even periodic intervals. So I'm quickly going to demonstrate this. For example, if an incoming packet with the flow ID B is received by the HashPipe, HashPipe will first insert this flow into the first stage. The flow and the count and the flow ID that was already stored here, so C5, will be sent to the next stage, and its count is then compared against flow in the second stage, so in this case T2. And the one that has the higher count is kept in the second stage, while the next one is processed by the third stage. So eventually, the flow with the smallest count is removed from the counting structure. However, we can see that the red counts, so the counts that were used to update the flow count, cannot actually help us to estimate the flow count for flow B. So we cannot, so the switch would now not be able to actually make a decision whether this packet belongs to a heavy hitter flow or not. To do so, we also need to access all these green counts. However, as we previously mentioned, programmable hardware has a certain amount of constraints, among other things, a limited amount of memory accesses per register array, so usually only one. And we can see that the HashPipe violates these constraints in both second and the third stage by accessing each of them twice. So in order to be able to estimate the count, a packet would need to be recirculated to the beginning of the processing pipeline, halving the throughput of the switch, which of course is never good. So there are other approaches, such as the count-min sketch. So count-min sketch works similarly. For each incoming packet, it first hashes its flow ID and then updates one count per each counting stage. So we can see this here. So in this example, it uses 4 different hash functions and it increases 4 different counts. Now, the count estimate is calculated as the minimum across all these updated counts. However, counting the minimum is not that trivial on programmable hardware, and to do so, we would need additional processing tables between these counting stages. So these processing stages would just compare the 2 counts and keep the minimum so that it can move through the pipeline. So this way, a minimum can be calculated, but this, of course, also means that we are using double as many processing stages as a solution that doesn't calculate the minimum. In addition, we can see that all these counting tables need to count up to the n, which is the window size, because, of course, we need to be able to count up to the maximum value. So to address some of these issues, we first started by considering an easier of the problem. So we wanted to see if we can improve the counting sketches on in an interval-based measurement approach. So we first tried to optimize the counting sketches to be more suitable for programmable hardware. And to do so, we designed our own approach, which is the Modulo sketch. So similarly to the count-min sketch, the Modulo sketch also works by hashing the flow ID of an incoming packet and increasing the count in the first table. However, it also compares the value of the count to a set of thresholds, so in this case 16, and if the count is actually equal to the threshold, the count will be reset to 0. The bit array value associated with this count in the first table is also set to 1, and the count in the next stage is increased. So this second stage now counts in the multiples of the threshold of the first stage. So each count from the second stage is worth 16 counts, basically. In addition, the same process continues. So then the second count is compared against the threshold, in this case 4. However, as it's smaller, the counting process stops. Thus, intuitively, the Modulo sketch works like a clock. So as it zeroes out the seconds, which in this case are our first stage, it increments one counter of the minutes, which is basically the second stage. It proceeds the same way by resetting the minutes. So the second stage by incrementing the hours. So if certain thresholds when certain thresholds are reached. Thus, for example, if here we would, if the second count would be equal to the threshold, we would reset that count and increase the count in the third stage. That would now count in multiples of the product of the 2 thresholds. So that would be 4 times 16, which is 64. We can see that a few things are different here compared to the count-min sketch. First, the first 2 stages count only up to the thresholds, so 16 and 4. Thus, the counters in the first 2 stages no longer need to count up to n, and that also means that they can be resized. So we need less bits to be able to count up to the maximum value in the first and the second stage. Thus, we are using the memory available on the switch more efficiently. In addition, we can see that the stages are sized differently. So we have a certain amount of, we have widths that we can customize. And in this case, we decided to add more counters to the first table because the first table processes all packets. However, as only a smaller amount of packets will reach the later stage, the amount of hash collisions is also reduced in the later tables, and their width can be reduced. Thus, we can, by reducing also the counts of the second and third table, we can also add more counts to the first table. Thus, we can decrease the amount of collisions in the first table. Finally, to actually estimate the count, we summarize the counts in all the stages, where we, of course, take into account that the later stages count in the multiples of the threshold. Of course, we can notice that we also have a bit array. The bit array makes sure that when we are estimating the count, we only read the next stage count if the threshold was previously reached at least once. So only if the bit is actually set at least once to 1, we would read the next count. So we make sure that the count in the next stage was at least once updated. So we first started by evaluating our interval-based approach to see if our counting structure is indeed more efficient than the related work. So in this figure, we can see that our modulo sketch, which is represented by the red and the blue dot, is actually able to achieve the better performance, especially when compared to the other related work, and has a lower percentage of false positives and almost zero false negatives. Similarly, even when we increased the memory to 15 kilobytes, we were still able to achieve better performance than the related work. So now that we have designed an efficient counting structure, we will extend it to also support the sliding windows, which was one of our main goals in this project. So to do so, we first split the total window n into small subintervals of size n divided by k. So in this figure, k is equal to 3. So we split the whole window into n divided by 3 subintervals. And we use k plus 1, so in this case, 4 counting sketches, where each of these counting sketches is counting in one of the subintervals. So at the start of the counting process, we start by using the first sketch. After n divided by k packets are processed by the switch, we switch to the second modulo sketch, and so on. So every n divided by k packets, and after every n divided by k packets are processed by the switch, we switch the counting structure, recounting, so the modulo sketch. So after n packets are processed now by the switch, we reset the first modulo sketch, so the first counting sketch, and start counting in it again. To do so, of course, we need the control plane intervention that can immediately flush all the counts. To estimate a count from using this window, we just summarize all the counts from all the sketches. I'll quickly demonstrate this. For example, if you are using the last sketch to count packets, an incoming packet would start first by reading the counts in the first sketch, as shown here. So as the count is equal to 10 and the bit index set to 1, we also read the second stage of the modulo sketch. Then we go to the second sketch, finally to the third sketch, and we finally reach our fourth sketch, in which we now actually add packets. So this is the sketch where we also increase the counts. So we also evaluated this approach and compared it to an approach that periodically resets the counting sketch every n packets, so to an approach that actually doesn't use sliding windows. And as we can see here, our sliding window had better performance at other related work by having a lower percentage of false positives and 0 false negatives. Moreover, it's important to notice that usually in the heavy hitter detection problem, false positives are considered to be better and have a less penalty than false negatives, because it's usually considered that it's better to falsely identify the flows than completely miss them. So in our case, our approach is only having the false positives, and even then a much smaller percentage than the percentage of false negatives by the related work. So as the next step, we wanted to see if it was possible to implement a sliding window approach without any control plane intervention. So currently, in the sequential window, as we described earlier, we need a control plane to reset one of the counting sketches every n divided by k packets. So every n divided by k packets, a control plane action is needed, and all the counts are flushed immediately. Of course, P4 programs, out of the P4 program, this is not possible. So we cannot, we don't have actions in P4 that would allow us to flush a whole counting structure. So to solve this, to be able to do this in the data plane, to exclude the control plane, we designed the zeroing window. So the main idea was to loop through all the counts in the sketch and reset the whole sketch so that all counts are reset every window size. Thus, every n divided by width packets, we reset one of the counts. I'll quickly demonstrate this. So first, we start by resetting the first counter. Then, after n divided by k packets are processed, we reset the second counter using a sequential index. This way, we effectively go through the whole counting structure and reset the whole effectively reset the whole counting structure each n packets. However, if you look at this picture, we can see a big problem. It violates the same limitations of the programmable hardware as the HashPipe, so it has two memory accesses per same register array. So as we also need to increase a count, we also need now to delete a count. And we are accessing first and second stage twice. To solve this problem, we designed a specific version of the zeroing window that addresses these issues. So we decided to split each table into two smaller tables. Now, based on the hash of the incoming packet, we reset one of the subtables. So for example, if you look at this picture, we can see that the incoming packet is hashed into the second subtable in the first stage. This means that we can reset the count in the first subtable of the first stage. And we do so. Similarly, for the second stage, the flow hashes into the second subtable in the second stage, and we flush a count from the first stage. Finally, we apply this mechanism to our sequential window to get our final solution. If you look at this, we can see that our sequential zeroing basically is very similar to sequential window. However, in contrast to using the data plane to reset one of the sketches, it uses the zeroing window. So for example, if you look at the same example we had previously with the sequential window, instead of only reading the packet in the first counting sketch, we also zero out one count. Similarly, the counts from the second and third counting sketch are just read, and in the last sketch, we also increase the counts, so similarly to the sequential window. Of course, every n divided by case, we also shift which sketch we zero out and which sketch we add packets to. So here, in the next interval, we would actually add packets to the first modulo sketch and zero out the second one. We also evaluated this approach, and this figure shows that our sequential zeroing window with the modulo sketch was able to increase the performance even further. So even compared to the sequential window, by having a very small amount of false positives and almost zero false negatives. Finally, to conclude, in this paper, we addressed the problem of sliding window heavy hitter detection. We started by first considering the easier problem, so the interval-based approach, and we built it up to finally reach a solution that can do so using the sliding windows entirely in the data plane. In addition, we verified all our results on programmable hardware, so the Netronome SmartNICs. These results are also available in our paper. So additionally, we also feel that similar techniques can be used for other algorithms in the data plane as well. So for example, zeroing through ping-ponging through the memories, sequential window, or counter reuse through Modulo. Thank you.